An alternative way to describe motion with constant acceleration is to use the constant acceleration functions. These are very similar to the constant acceleration equations. The derivation parallels them in many ways, but there are a few key differences here. The idea is that if the acceleration is constant and the acceleration is the derivative of velocity, then a constant acceleration indicates a linear velocity. If we do an antiderivative, if we do another antiderivative, then the position should be a quadratic or a parabolic function. So what we can do is find the position and velocity as functions of t, doing a more sort of formal derivation rather than looking at a fixed interval like we did with the constant acceleration equations. The reason that we make this distinction is that this definition is better for a poorly described interval. Basically, when you have two objects that are moving and they're meeting at an unknown place or they're meeting at an unknown time, it's difficult for us to express what the displacement is or what the elapsed time is, because we don't know those values when we're setting up the equation. If we use these equations instead, we can say the two objects meet when their positions are the same at the same point in time. And so this sort of sets us up for more of the traditional algebra and solving problems like we've seen before. The acceleration is the derivative of velocity, so that's going to be the slope of the velocity graph. Acceleration is the second derivative of position, and so that is going to show up as the curvature of the position graph. Velocity is itself the derivative of the position, so the velocity is going to show up as the slope on the position graph. We're going to assume that the acceleration graph may be discontinuous. We're going to assume that an object can immediately change its acceleration. For example, if you are accelerating in your car and you slam on the brakes, you can assume that your acceleration is instantaneously going from speeding up when you're hitting the accelerator to slowing down when you hit the brakes. In real life, there's a little bit of a change there, but we're trying to keep a simplified model as much as possible. Even if the acceleration is discontinuous, however, the velocity graph must be continuous. If you are changing your acceleration, that means your object is speeding up or slowing down, but the velocity has to be a continuous value. It can be continuously getting larger, it can be continuously getting smaller depending on the acceleration, but it has to be a continuous function. You can't immediately switch velocities without crossing all the other velocities in the meantime. Another important point is that since the acceleration is the second derivative of the position, that means the position graph has to be continuous and also differentiable. By differentiable, we mean smooth, that you have smooth transitions from one portion to another portion with no sharp points where you wouldn't be able to find the slope of a tangent line. So let's see what that looks like in practice. Here is what the graphs would look like. We said that you have constant acceleration should be a horizontal line. A horizontal line represents a constant value. So we have an interval of constant acceleration, another interval of constant acceleration, and another interval of constant acceleration. So we can use the constant acceleration functions to describe this portion, and then this portion, and then that portion, and we can look at each one separately. We see here that the acceleration is large and negative, and we can see how that shows up in our graphs as well. Notice that the velocity has a large negative slope there. The velocity has zero slope here, corresponding with the zero acceleration, and the velocity has a small positive slope there, corresponding to this portion. We can also look at the position graph. We can look at concavity based on sort of sketching in a parabola. We see that we have, for a large negative acceleration, we have a narrow downwards facing parabola there. For a positive acceleration, we have a concave up parabola facing upwards. For a small acceleration, notice that this parabola is much wider than this parabola. This parabola is much narrower. It changes more quickly when you have a larger acceleration. We also see here that the velocity hits zero right about there, and that corresponds with our maximum value. We have another here, and we see the maximum value. And if we look at the velocity, we see the velocity getting, it's very steep, it's very large and positive like we have here. It's positive, but it's less. It's still positive, but it's even closer to zero. And then it actually hits zero. And we can track those values. We have a straight line portion here, which corresponds to a constant velocity and zero acceleration. And then we see the same thing here. The velocity is negative. The velocity becomes less and less negative until it hits zero. And now the velocity starts becoming more and more positive, which is what we see in that portion of the graph. So we can see how these individual sections relate to each other. When you're trying to graph these, the important part is to know where you are and at what point in time. So if we were going to graph these, we would likely know the beginning and ending points of these different intervals. And what we'd have to do is we'd have to know if the acceleration is negative, that's looking like a downward facing parabola. If the acceleration is positive, that looks like an upward facing parabola. And then we know that the graph has to be continuous and differentiable. Notice how we go from a parabola here to a straight line there, and notice how it's smooth right at that changeover. Same thing here, we have a parabola here, we have a straight line there, and again, notice that it's smooth there right at that changeover. The velocity graph is not smooth. The velocity graph is not differentiable here at this point because the acceleration is discontinuous, but the velocity here is a continuous function. So you can see that in these graphs when you're making your own velocity and position graphs. You'll know the few points where you're at, and you'll have to make sure that you are continuous and or differentiable as needed.